last two talks. Sure. First, Justin will tell us about zkVMs. Yeah. Different approach to do zkVMs than what we saw before. And then the last talk will be about zk.
Great. I'll try to talk loud. Okay, so I'll start at the beginning. I want to tell you about new arguments for memory checking. But starting at the beginning, this talk is about SNARKs, right? So probably the 10th time you've seen this defined in this workshop, but just for a self-contained talk. SNARK is a cryptographic protocol that lets an untrusted prover prove it knows a witness satisfying some property, right? So the trivial proof is for the prover to just send the witness to the verifier, and the verifier to directly check that the witness satisfies the property. And a SNARK is a cryptographic protocol that improves those costs for the verifier, right? So ideally, the SNARK proof will be shorter than the witness itself, and checking the SNARK proof will be faster than checking the witness directly. So throughout this talk, I'll call checking the witness directly, I'll call that native execution or witness checking. Yeah. All right, so just to have a high-level picture in your head about how SNARKs might work in practice throughout this talk, imagine a developer who knows nothing about SNARKs writes the witness checking procedure in their favorite programming language, right? And then that high-level program gets automatically compiled down into a low-level representation that the SNARK proof machinery is able to ingest. And this is typically a circuit or something, right? And then the SNARK will then directly prove that the prover knows a satisfying assignment to the circuit, right? So we call the first step, the thing that turns like the witness checking procedure into something like a circuit, we call that a front end. And we call the second step, directly proving the circuit, we call that the back end. And the line between front ends and back ends can sometimes be blurry, but it does help to sometimes separate the two. Okay, and in terms of where SNARK performance is today, and prior talks in the workshop have discussed this a little bit, but briefly, verification is generally cheap. At a minimum, the proof is actually shorter than the witness, unless the witness is really, really tiny, and checking the proof is faster than directly checking the witness, right? Again, unless it's sort of an almost trivial statement being proved. Now, that doesn't mean there's not significant variation in verifier costs, right? There can be more than 2 orders of magnitude differences, but nonetheless, it's generally, interesting for the verifier. The costs are, in a cosmic sense, quite cheap, much cheaper than native execution. So it's the prover where the main scalability bottlenecks are today, right? And so in general, SNARK proving today, and everything so far is actually verbatim from my bootcamp talk, but we'll quickly move beyond that. The proving is in general about 1 million times slower than just running the witness checking procedure with no proof, right? Now, to be clear, this million-fold overhead that the prover incurs is highly parallelizable, but even so, no matter how many GPUs you throw at it, it's still limiting the applicability of the SNARK to have the prover doing 1 million times more work to come up with the proof versus to just run the program with no proof of correctness. So I know Ron's talked a lot about applications to the Ethereum blockchain, but generally, the main application there that people are focused on today, proving Ethereum blocks, they're proving like a fraction of a second of sequential, serial runtime on your laptop, right? It's really not much work they're proving, and yet it takes 100 GPUs or something like that to prove that in under 12 seconds. Right, so you're just seeing the result of million-fold overheads. You need a lot of GPUs to parallelize that away. And so I do think that this million-fold overhead is falling by 1 to 2 orders of magnitude kind of as we speak. And I want to tell you today about what I think are some of the most promising techniques to achieve that. Okay, so very brief overview of SNARK backend design, still sort of at the bootcamp talk content, but again, quickly moving beyond it. So generally, there's a 3-step recipe for designing SNARK backends, right? First, you design what's called a polynomial IOP. Then you design a polynomial commitment scheme, which is a cryptographic protocol. You can put these two together to get a succinct interactive argument. And then typically you use the Fiat-Shamir transformation to eliminate the interaction and get a SNARK. And we've heard a lot about, open questions about the security of that, but that's generally the recipe that we follow. And so just what is a polynomial IOP in a slide? This is actually a special case of a polynomial IOP that sort of suffices for everything I want to tell you about today. So the prover's first message in the protocol specifies a polynomial that's pretty big. So if the prover actually sent it in full to the verifier, say by listing all of its coefficients, you wouldn't have succinctness. The proof would be too long. Okay, so we don't actually let the verifier read the whole polynomial. The verifier is only going to be allowed to evaluate the polynomial at a single point of its choosing later in the protocol. Okay, so after the prover sort of sends this polynomial to the verifier and the verifier doesn't get to read it all, then they engage in sort of a standard interactive proof, where the verifier is reading the entire prover message. And at the end of that interaction, that's when the verifier sort of picks the point it wants to evaluate the original polynomial at, and the verifier gets that evaluation. Okay, so generally speaking, this big polynomial from the first message, this somehow encodes the witness. And the point of the second part of the protocol, the interactive proof, is to prove that the encoded witness is a valid witness, right? And so you could kind of think of the second part of the proof from the verifier's perspective as a reduction from the global claim that the whole witness is correct to a local claim about like a single evaluation of the encoding. Okay. And so high level, there are two classes of polynomial IOPs, one in which the underlying like algebraic machinery that the proof system is made out of is univariate polynomials, and the other in which the polynomials used are multivariate or multilinear. Okay, and just very high level, the univariate polynomials are better for verifier costs, and the multivariate ones are better for prover costs. This is still a little bit of a controversial statement, but hopefully I'll make a good case for this during this talk. And even in the the sort of the high verifier cost case, the verifier costs are not that high. Think of proofs that are maybe a couple dozen kilobytes in size, and you can always bash the proof size down via SNARK recursion, sort of using a smaller proof SNARK to prove the slightly bigger proof, if you're willing to use that technique. Although one sort of theme of the talk today is efforts to sort of get rid of recursion, and so I do hope that in the long run we sort of decide we're happy with slightly bigger proofs, so that we can have fast provers and not have to use SNARK recursion to bash the proof size down. Okay, and so a polynomial commitment has been talked about many times during this workshop, but just in a sentence, it lets the prover succinctly bind itself, succinctly commit to a big polynomial, right? So the commitment is just like 32 bytes or something, right? And then later reveal a requested evaluation of the polynomial along with the proof that the requested evaluation is correct. Okay, so this is exactly what you need to turn a polynomial IOP into a succinct argument, because that big polynomial that the prover sends in the first message of the polynomial IOP, this lets the prover just send a short commitment to it, and later when the verifier wants to get an evaluation out of it, the prover can give the evaluation. All right, so there's many classes of polynomial IOPs, and they generally give different trade-offs between the cryptographic assumptions on which security is based and prover time and verifier costs. And there have been a bunch of talks about this, and I talked about this at length in the bootcamp talk, so I don't have much to say about it right now, but I'll elaborate on this later. Okay, so now we're moving past sort of the more standard prelims and into the new content. So I want to tell you what these twist and shout memory checking arguments are, basically like what problem they're solving and what their interesting performance profile is. Then I'll tell you their applications to zkVMs and a particular zkVM called Jolt. I'll then briefly discuss the notion of streaming provers, which again, it's a way to control prover memory usage without bringing in SNARK recursion. And twist and shout are kind of a big unlock in this direction. And then with whatever time I have left, I'll actually tell you how twist and shout works. So everything in the first three parts won't be all that technical, and then the fourth part will be quite technical. Okay, before I get to any of this, I want to just tell you in advance what the key takeaways are, what I kind of hope to convince you of today. So one is that the SumCheck protocol is kind of the key engine behind fast prover SNARKs. right? And why is this high level? It sort of minimizes the amount of data the prover has to commit to, and then also minimizes the amount of time the prover has to spend to prove that the committed data is sort of well-formed or valid. And I will be trying to unpack this intuition like at deeper and deeper levels throughout this talk. Then a second piece of intuition is, or a takeaway here, is that like not all applications of the sum check protocol are sort of equal, right? And in particular, the fastest and simplest SNARKs, they exploit repeated structure in computation. Okay, so what I mean is, if the prover is claiming it ran the same simple procedure like a billion different times, okay, it can prove that faster than proving it ran some completely unstructured procedure of the same time or size bound, right? And if we do not leverage this repeated structure that exists in the computation, we're sort of leaving, fuel there that we could have burned for speed and simplicity. Okay, so that's this talk is a running theme throughout the talk. Identifying repeated structure in computation and sort of exploiting it to the max for simplicity and performance. Okay, and then in terms of how we unlock that repeated structure to the to the maximum extent possible, so this is a little bit more in the weeds of the takeaways, is there are sparse polynomials everywhere. So these are polynomials that might have, say, very high degree if they're univariate, but most of their coefficients are 0, right? And most prior work sort of doesn't like the sparsity, right? What they'll try to do is they'll try to get rid of all those zeros. Yeah, and so the message here is don't get rid of them, embrace them, okay? So just ensure that the prover never has to pay for those zeros anywhere, right? Now remember, any SNARK has sort of two components, right? There's the polynomial commitment scheme and there's the polynomial IOP. So we need to avoid paying for those zeros in both components, right? And so there are some commitment schemes that are really, really good at not paying for zeros. And I'll explain this shortly, but if you're familiar with elliptic curve commitment schemes, like literally the zeros can just get filtered out. And then there are sum check proving procedures where if you have a giant sum and almost all the terms in the sum are 0, the prover just ignores the 0 terms as well. So you put these two things together and now neither component of the SNARK is paying for those zeros and you're good to go. Right? So the message here is don't get rid of the zeros. You could do that, but there'd be some overheads. Instead, just embrace them and don't pay for them. Okay. All right, so let me tell you what shout is. So I'm going to present it as what I call a batch evaluation argument, although most people would call it a lookup argument, and they're just two different perspectives on the same kind of protocol. And actually, both perspectives are valuable, but let me start with the batch evaluation argument perspective. So we're going to consider any function f. Say it takes two inputs, x and y. Let's say each of these inputs are, say, 32-bit values. And some of the applications I'm most excited about, this function f will just be like a primitive instruction for a simple CPU. And so when I say x and y are two 32-bit values, I really mean they're values that can be sort of stored in a single register. Right, because CPUs, what they do is each primitive instruction, just gets applied to two values, one in one register and one in another register. Okay, let's imagine for the moment that the prover has committed to t different input pairs, x1, y1 up to xt, yt, as well as t claimed outputs, z1 up to zt. Okay, and the claim is just that every zi is just the actual output of f applied to the associated input xi, yi. Okay, this is you're evaluating the same function f on many, many, many different inputs. Questions about the setup? All right. So the standard way of proving a statement like this is to just take a circuit for f and lay t copies of it sort of side by side and apply your favorite SNARK for circuit satisfiability or evaluation or whatever. Okay, and all right, so this has a couple downsides. One is there's a circuit here, and circuits can be complicated, and surface area for bugs and things like that. And the other is, so that's a simplicity issue. The other issue is performance. So even if you apply sort of the fastest known SNARKs for circuits, you're still going to have the prover doing about 6 field multiplications per gate of the circuit. Okay. And you know, that's assuming, you know, there's no like untrusted advice needed to keep the circuit small. You know, most of the time there would be like a lot of, you know, you take this value and you decompose it into bits or limbs, and those bits or limbs are untrusted advice, and the prover has to pay to commit them as well, right? So yeah. So that's sort of the traditional way of doing batch evaluation arguments, and there are, you know, this is a very, very structured circuit, and there are ways to leverage that structure, but they're sort of limited, right? They, yeah, they can only get you so far. All right, so a batch evaluation argument just cuts the circuits out, right? And so here's how to think about the costs. So shout is a batch evaluation argument. You should think of the prover as paying a fixed cost, which does not depend on the batch size, okay? And then on top of the fixed cost, it pays like a per evaluation of F cost, right? So that's, you know, so the total per evaluation cost over all the evaluations, of course, does, you know, so if you're paying C field ops per evaluation, you pay C times batch size in total, right? So the fixed cost, you know, can be pretty big because that cost gets sort of amortized across everything in the batch. Right, okay. So in general, what is the fixed cost? So this cost that depends only on like the number of possible inputs to F and independent of the batch size. So you can, you know, let capital K be the number of possible inputs to F. So, you know, if these are 32-bit inputs, capital K is like 2 to the 64. Okay, so the fixed cost depends only on K. Right, and with shout, the fixed cost can be kind of any power of k. So k to the 1/2, k to the 1/4, k to the 1/8. Right, and you know, there's a tension here. It's right, like the bigger you make the fixed cost, that is the lower this power 1 over, the lower the c here in this power 1 over c, the smaller the, sorry, I get it. Big fixed cost means small per evaluation cost. Small fixed cost means large per evaluation cost. Yeah, so if you want C greater than 1, you need F to have some structure to it. I don't think you can, you know, if F is totally unstructured, there's just no way to make C less than 1 in general, yeah. But, okay, so, you know, yeah, okay.
Let's say C is 2, and it's allowed to be 2. So now we have 2 times T times some constant underneath, I guess some reasonable constant.
Yeah.
So I don't know, let's say 10 times T or whatever. And you want to compare this against the 6 times T times the circuit size that you had before. And
yes.
So you're saving the circuit size.
Yes, you're saving, yeah, exactly.
And the constants underneath are comparable?
Yeah, I think this constant in general is very reasonable, and then, you know, I think it might even be like 4 or something like that. Yeah, so concretely, I will state what it comes out to in a moment, but that's the exact comparison to make, yeah, on the performance side. That's right. Other questions? Yeah, so to make C bigger than 1, you do need structure.
And you're doing just like C lookups, I guess.
Yeah, exactly. Sorry, capital T lookups. Yeah, and right. I mean, to elaborate on what the structure is a little bit, it's a little hard to convey. But if you're familiar with the lasso work, which predates shout, that did have this property of breaking one lookup into.
Yeah, I think it was already in Zcash. Yeah, yeah.
Okay, yeah. So that's where that C is coming from. But in shout, that kind of decomposition of you know, one lookup into a big table into C lookups into smaller tables, it's not in the protocol at all. It only comes up in the prover algorithm to make the prover fast.
Okay.
Right. Whereas in Lasso, it's baked into the protocol. The prover is actually in Lasso committing to the, you know, decomposition or whatever, and that shout gets rid of that. And that's where a lot of the benefits of shout over Lasso come up. Okay. Yeah. So right. So. Yeah, I'm waving my, so you know, ultimately I want F to be like a primitive instruction for CPU, and like all natural CPUs, like their primitive instructions all have the properties needed to let C be whatever you want it to be here. Other questions? Okay, so yeah, so the comparison, you know, in a concrete example is the following. You know, so let's consider, you know, the function takes 2 32-bit inputs, so the capital K is 2 to the 64. let's say the number of evaluations of F is like 1 billion. You should think of this number as something like the number of CPU cycles you're proving you ran a CPU for. And CPUs today, they run like billions of cycles per second. So like 1 billion cycles is a quarter second of work on a laptop or something like that, single-threaded. And so then you might set C equal to 4. Okay, and that means the fixed cost would be like 2 to the 16 of that order. But that's negligible compared to the per evaluation cost, which is some constant times 1 billion, right? 2 to the 16 is like in the hundreds of thousands. It's just like ignorable compared to the, yeah. So that's the parameter setting you should think about. And what this translates to concretely when you work through all the constants and all that is like 100 field multiplications per evaluation. Okay, and that's comparable to like our fastest SNARKs for deterministic circuits applied to, I don't know, like 15 gates or something. Okay, and roughly speaking, there's not much you can do in 15 gates other than literal native field operations, right? Like a field multiplication is obviously one multiplication gate, so you can do that in one gate, but there's not much more you can do in just like 15 gates, right? So that's the rough reason to think that this has hope of being a significant prover speedup. Okay, questions? Okay, so I want to give some intuition for why this might actually beat SNARKs for circuits, like what's really going on here. And I think that two pieces of intuition are useful. One is we're seeing an economy of scale here, right? We're like paying some fixed costs, think of that as like building a factory. Once you build the factory, it's pretty cheap to put out more widgets, right? So with SNARKs for circuits, sort of there is no fixed cost. Even if you're proving just one application of F, you kind of pay the same per gate price. So you might think that paying some kind of upfront cost should buy you something, and that's indeed what we're seeing here. The other piece of intuition is that these lookup arguments, these batch evaluation arguments, they don't tie the prover's hands as tightly as circuits do. Right? When you have a circuit, the prover is proving it evaluated F in a particular way by going gate by gate through a circuit. With these lookup arguments, the prover is not saying how it got the F of X comma Y at all. It's just saying, here's the output. I'm not telling you how I got to it. Yeah, and so the tighter you tie the prover's hands, the longer it's going to take the prover to work its way to a correct proof. And so that's another thing that's going on here. I'm sorry?
What's your comparison? Like, are you comparing to a SNARK applied to the entire?
Yeah, I'm comparing to a SNARK applied to this circuit here. And so this SNARK would be proving that the prover evaluated each copy of F by going gate by gate through a circuit. And lookup arguments, batch evaluation arguments would not be doing that. The prover would be saying nothing at all about how it actually went from the inputs to the outputs.
What's a useful C to keep in mind? Just to represent.
Yeah, so C equals 4 is a nice one.
No, sorry, capital C.
Oh, capital C. Yeah, so bitwise AND, bitwise OR. So if think of X1 and X2 as like individual field elements that you then want to take their binary representation and bitwise AND it, and then pack that into a single field element. And so yeah, so just for everyone's so the traditional way to do that, and there are people have gone beyond this, but by now, but you would just commit to the binary representation of X1 and Y1. That would be 32 committed bits for total. Oh, sorry, for each, so 64 committed bits total, and then you would do bit by bit the bitwise AND. And so you'd wind up with 64 committed values and 64 gates or something. And shout is equivalent to 0 committed values and 15 gates or something like that.
Plus you have to check that they're really bits.
Yes, and I forgot that too, yeah. So even more speedups for shout, yeah. Okay, yeah, thanks. Other questions? Okay, yeah, so that is the intuition for what we're sort of leveraging here and why we can hope to beat circuits. And now here's a different perspective, which I've sort of verbally been switching back and forth already, but let me make it clear. So we can think of a read-only memory of size k that literally stores the entire evaluation table of F, right? So for every possible input to F, here's the output. And then an evaluation of F is just a lookup into that read-only memory, right? And so from that perspective, people call these lookup arguments instead of batch evaluation arguments. Okay, but I think the way lookup arguments sort of most naturally get applied in something like a zkVM, they really are acting as batch evaluation arguments. Okay, I think the lookup argument perspective came when the tables people can handle are sort of limited in size, you know, but batch evaluation, the table is huge, right? And so, you know, anyway, that's just some speculation about why people might have arrived at one perspective versus another. Both are valid, both are important. Yeah, and so in the read-only memory perspective, the fixed cost is depending on the memory size, independent of the batch size, the number of lookups, and then the per evaluation cost is really a per lookup cost. Okay, so that the reason I'm introducing this perspective now is the way to introduce this second protocol twist. Yeah.
Does it make sense at this point to talk about V cost as well? Because are there trade-offs on the verifier side, or this is all that?
Yeah, I'd say that. Well, okay. So for shout, the verifier cost is logarithmic in K and T, and this actually tends to be better than the circuit-based approaches that had the fastest provers before shout. And why is that? It's because the fastest SNARKs we have for circuits today are like the gCarry protocol, and they have log squared proof size, so they'd be something like log squared T. And with something like shout, you get, you know, just log K plus log T.
Okay, but either way, the fact that K is under a log and T is under a log means that you can play with parameters here on the prover and the verifier barely feels it.
Yes, exactly, that's right.
But
Yeah.
C will be linear in the verifier.
See, yeah, let me think about that for a second. So, no, actually the C is only felt on the prover side. Okay, this gets a little, later in the talk there will be a different parameter. So this C here is controlling prover cost in sumcheck. In order to control certain prover costs in commitment scheme, we will have a different parameter D, okay? And they tend to be almost the same because they're both controlling the same kind of cost, but in two different parts of the protocol. And that D is felt on the verifier side. This C is not. This C only exists in the prover's head.
Okay, thanks.
Yeah.
So you're not assuming that this table is kind of described by a small circuit?
No, I will say this, to get C greater than 1, we need some structure, and that structure probably implies that the table is described by a small circuit, but then the actual protocol never refers to that circuit. Okay. The structure is purely exploited in the prover's head to make its runtime fast. The protocol itself doesn't care about the structure. The only thing that the verifier needs to be fast in this protocol is just that what's called the multilinear extension of this F is quickly evaluable. Okay, and that's also a kind of structure. Yeah, that's a good, but it's a pretty mild structure. Yeah. Other questions? Great. Okay, so twist. Yeah.
Justin, if you look at arithmetic things like computing, I know, square root, is it obvious that the multilinear extension is fast?
So something like, okay, so you're saying like map x to square root x?
Yeah, I mean, in general, you need the function to be super simple.
Yeah. I mean, yeah, the right intuition for like what functions have quickly evaluable multilinear extensions is functions whose output is like a simple expression of the bits of the input. You know, they have simple multilinear extensions. That's waving my hands. You know, Ron and Justin Holmgren have like a formal sufficient condition in terms of read-once branching programs. Yeah, if you have a function that whose multilinear extension is not quickly evaluable, you are not directly going to be able to apply shout to it. But you know, most of those functions, you know, can get broken down into a relatively short sequence of shoutable, MLE structured things, right? So like if F is like SHA-2, right? SHA-2 is like sort of designed to be pretty unstructured. And so its multilinear extension is, there's no way that's quickly evaluable. But you look at like the pseudocode for SHA and, it's, you can, each thing that you see in that pseudocode is sort of MLE structured and shoutable. It's bitwise AND, bitwise XOR, sum modulo 2 to the 32. All of those things are nice. Does that help?
Yeah. I mean, but things like div, even basic instructions like div, I would guess.
Well, div you would do a little bit of untrusted advice and provide the quotient and and then the check is just a multiplication, and then that is nice and shoutable.
Okay. Yeah, thanks.
Okay. More questions? These are great questions. Okay, so twist. So twist is a generalization of shout, and we really want sort of the memory checking perspective for twist. So shout is for read-only memories, twist is for read-write memories, right? So here's how I would think about twist. Consider a CPU that every CPU cycle it's doing like one read to RAM and one read from RAM and one write to RAM. Okay, every time a read to RAM is done, that read returns some value, and the prover is going to have to prove that the value returned is the right value. What is the right value? It is the value last written to the cell that is now being read. Okay, so the setup would be here, like the prover is committed to T different write addresses and write values, saying, hey, at time 1 I'm writing this value to this address, at time 2 I'm writing this value to this address, and so forth. And similarly, the prover is committed to read addresses and read values. And again, the key thing to prove is that the read values are correct given the writes. Questions about that? Okay, so twist does this. And here I have its costs on the slide. I don't want to dwell on them too much. I will mention, so in the worst case, the prover pays log memory size field operations per read or write. Okay, but if the memory accesses have some locality properties, each memory access, you sort of only pay for the locality property and not for the whole memory size. Right, so if your reads and writes are just all over this huge memory, then you will pay, log k field operations on the prover per access. But real memory accesses tend to have be local, and then you'll pay nothing like that. Okay, so then concretely, we find that the twist prover is maybe 3x faster than the fastest known prior works, but also has shorter proofs than them. And then if you compare the twist prover to prior works that had comparable proof size, the twist prover is actually more like an order of magnitude faster. So you either sort of improve noticeably on both axes, or you improve a ton on one axis and leave the other axis the same. Another benefit is the twist prover is very streaming friendly, and I'll say more shortly about what that means. Okay, so yes. Yes, unless I just eat up all my time telling you what the results are. Yeah. Okay. So and I'll try to get to the protocols quickly from here on out. Okay. So we came up with these protocols in the context of designing zkVMs, and these, well, Ron's whole talk was also on zkVMs. These are SNARKs for the prover proves it correctly executed a computer program correctly, kind of cycle by cycle, where each cycle is for a simple CPU. Right, and the CPUs they only sort of do two things over and over, right? They call fetch the next instruction, decode it and then execute it, or they do reads and writes to memory. And so there's been a ton of work on zkVMs recently, and the big challenges here are prover overhead, and they're just very complicated. So all the zkVMs today still definitely have bugs in them, and people are working very hard to address this, but these are the two challenges. So the message here is prover performance is a big deal, and simplicity is a big deal. Okay. And so there's been a big focus on RISC-V zkVMs. I would say why RISC-V? Ron also talked about RISC-V. So one reason is it's sort of the simplest CPU architecture that came from this computer architecture community, right? And so it's hard enough to build these zkVMs. We clearly should start with kind of the simplest thing available that has significant use, and that is RISC-V. And given that it was designed from outside the SNARK community, we can kind of make use of existing tooling, and we don't have to rewrite compilers from scratch and all of that. The other reason is, and this is a controversial statement, it's actually pretty SNARK friendly. And we'll see why it's SNARK friendly, but one reason is like every RISC-V primitive instruction has the kind of structure that shout needs to work. Right, so it wasn't designed with a batch evaluation SNARK in mind, but it happens to have the structure that the batch evaluation SNARKs need. And then there's also a focus in the blockchain community I want to mention on proving like blockchain blocks. And the main thing I want to note here is like the number of RISC-V cycles that processed by like an Ethereum block today is about 1 billion. I want to put that number in your head just because that's the that's why I was using 1 billion as an example of the number of lookups before.
So the RISC-V architecture and the instruction set actually differentiates between writing to registers and writing to RAM.
Mm-hmm.
Yeah, that's just because it came from the hardware world. But in the zkVM world, is there a difference between writing to registers and writing to RAM?
Right. So you sort of have an option to just treat the registers as part of memory or not. In Jolt, we are treating the registers as separate. And why do we do that? It's because that T log K runtime for the twist prover, log K is memory size, and that's really, really small if the memory size is tiny. And so with 32 registers, T log K is like, really nice. This is just one example of, some increasingly bizarre coincidences where decisions made by real hardware designers turn out to be exactly the same decision like I would have made if I was designing a VM for SNARK friendliness. And yeah, so the parallels between how you would design for SNARK proving and how you would design for real machines seem to go strangely deep. Other questions? Okay. Yeah, and just to be, so registers are read and written like pretty much every cycle. In fact, you read 2 registers and write 1. And then RAM is accessed, not every cycle. And even when it is accessed, you only do 1 read or 1 write. And so registers are really key. Like with the way we came up with twist and shout was we were looking at Jolt today, and we were like, well, once everything is optimized, like the bottleneck is going to just be reading and writing registers. And this feels really silly because there's only 32 registers. Like, surely we should be able to leverage that there's only 32 of them. And the existing memory checking arguments don't benefit from that, really. And so we sort of were like, well, what if you literally only had like 3 registers, forget 32, just 3, what would you do? And then it turned out what we came up with actually is really effective even for big memories. Okay, so Jolt is a zkVM that's sort of uniquely designed around like the sum check protocol, and now more and more people are using that protocol, but batch evaluation arguments in particular. And we're doing this both for performance and simplicity. Okay, and I'd say the key insight is like VM execution is like the very epitome of repeated structure and computation, right? The VM is just doing fetch, decode, execute over and over and over again and reads and writes to memory. It's the same simple thing over and over again. It's really asking for a batch evaluation argument, right? Okay, so here's Jolt in like one slide. So real CPUs have 4 components, right? There's registers and RAM, like you said, Dan, and we separate them out. There's executing primitive instructions. Right, and then there's the program bytecode. So that just means like, at each CPU cycle, you have to figure out like what's the next instruction to execute. This is the computer program that tells you that answer, right? And so just as with real CPUs, Jolt has these 4 components. So it uses twist for read-write memory. And this is sort of interesting. So for primitive instructions, we use the shout batch evaluation argument. And then for reads into the bytecode, we also use shout, but the right perspective there is as a lookup argument. So it's kind of funny that VMs bring up both perspectives on the batch evaluation lookup arguments. Yeah. Okay, and then there are no circuits other than to kind of glue these 4 things together. Okay, so there's a R1CS. It has 26 constraints per RISC-V cycle. And it's there to make sure we're sort of feeding the right inputs into each of these 4 instances. So you could just think of it as like a minimal glue. Alternatively, you could think of the R1CS or what we use to prove it as doing the real work, okay, but then like not checking a lot of stuff and then relying on like the 4 kind of external procedures to check that stuff, right? So it's kind of taking for granted that like the claimed output of every primitive instruction is the right one, and then it's shout that actually exogenously proves that. Okay. All right, yeah, so generally we're trying to minimize the use of circuits here, like that's the philosophy. And this is just an example of one of the more complicated RISC-V primitive instructions. This is all the Jolt verifier needs to know about the instruction, right? So like, alternative approaches that go through circuits, the Jolt verifier has to know a whole circuit implementing the primitive instruction, and that's complicated and bug prone. Here, what this code is doing is it's just evaluating the multilinear extension of the primitive instruction at a single point, and it's just, like 4 lines of code or something. So for getting performance, I would advocate for batch evaluation arguments based purely on how simple the verifier is. Just you're getting rid of the circuits more or less. Okay, so we spent the last 6 months switching Jolt over to twist and shout from other memory checking arguments, and the implementation is like just about complete. Like end of today, it might actually be running end to end, that sort of situation. So I can tell you some preliminary performance results. So the proof size is going to be like 50 kilobytes. We could bring this down more with recursion or just by increasing the prover time, but compared to like hashing-based, so we're not using hashing-based commitment schemes, we're using elliptic curves. 50 kilobytes is smaller, so I'd love it to be lower, but that's what it is. So I'm anticipating like once fully optimized, we're going to look at like a million RISC-V cycles per second proved on like a laptop. I think we're going to need kind of all of the optimizations we know about to be implemented before we hit that. But right now, we're already pretty close to about half of that. Okay, so like 500,000. This is already a significant improvement over the previous state of the art. Now, one thing I want to clarify is Jolt is all about these economies of scale, right? So the more cycles you're proving, the faster you can prove each cycle. So when I say I'm hoping for 1 million cycles per second, I mean on like not too tiny executions. So say 100 million RISC-V cycles are up. Okay, but remember, like proving an Ethereum block today is 1 billion cycles, and Ethereum wants to like 100x that in the coming years. So 100 million cycles and up is like not that big a restriction. I do expect Jolt to also be state of the art at like tiny executions, the kinds of things that come up in a lot of privacy applications, like I know a digital signature and stuff like that. But the prover will be a little slower, maybe 2x slower or something like that. Yeah.
No pairings here, just like prime order groups.
No, we're using pairings.
There are pairings.
Yeah. Mm-hmm.
And what is your view on now designing something that is pre-quantum versus post-quantum? Like Ethereum is particularly maybe paranoid on this matter.
Mm-hmm.
That's their view.
Yeah.
What's your view?
Yeah. Okay. So my view is that the real worry in the next decade is bugs, right? And the Jolt approach is simpler, and therefore more, amenable to hardening against bugs. Okay. Now I do want a post-quantum version of Jolt eventually. At the moment, I'm actually most optimistic about getting there with lattices instead of hashing.
Due to the way they can handle zeros.
Yes, exactly. That's right. So that's my
Very good. Thank you.
And you started with the slowdown factors. So what kind of slowdown factor is here? Okay.
Great. Yeah. So, right. So, assuming my expectations about Jolt performance come to pass, and I could be off by as much as a factor of 2, just because we're not at 1 million cycles per second yet. The Jolt prover will be doing about 40,000 times more work than native execution. I think this is what you're asking about. Yep. And there are kind of 2 ways to see where this 40,000 number comes from. So, like empirically, the clock rate of laptops today is like 4 billion cycles per second. And I'm predicting the Jolt prover will get to single-threaded like 100,000. That means parallel. It would, we get like a 10x parallel speed up. So with 16 threads or something, we get to 1 million cycles. With 1 thread, we're at like 100,000, right? So you look at the cycles per second the laptop does, divided by the cycles per second we can prove single-threaded, and that gives you an extra overhead for the prover. That's 40,000. Another way you can see it is analytically. So you can just like count the number of field operations the Jolt prover does each cycle, and it's about 500. And these are multiplications in a 256-bit field. Those take about 80 CPU cycles per multiplication. And so you multiply those together and you get a 40,000 fold overhead. So that is, I expect it to take 40,000 laptop cycles to prove 1 RISC-V cycle. Okay, and just for comparison, I'll mention, like Planck is a SNARK for circuits, right? Now, it's mostly optimized for verifier cost, not prover cost, but it is still popular. So just to put this all in perspective, the Planck prover does about the same number of field operations per gate in an arithmetic circuit that the Jolt prover does per RISC-V cycle. Right? So roughly speaking, this means, right, like unless the thing you're proving is directly a circuit, it's like directly natively doing field operations, probably the Jolt prover will be faster. Broadly speaking. Okay, so that's just a way to compare to something people are more familiar with today. Let me briefly, how much time do I have left, Dan? Like 10 minutes, 15? No, all right, Abhishek. 15? Okay, that's fine.
5 minutes.
Okay, that's plenty of time. So, okay. So I want to highlight attempts to get rid of recursion to the extent possible. And so twist and shout like magically seem to unlock this with minimal overhead. Okay, so the prevailing way to control SNARK prover memory usage is the following, right? Like if you're proving you correctly ran 1 billion cycles of a CPU, and you don't use recursion today, you're going to need like terabytes of space. Okay, like the prover space just grows linearly with the number of cycles proved. 1 billion cycles times whatever gives you terabytes of space, right? And so what people will do is they will shard the 1 billion cycles into, say, a bunch of shards with 1 million cycles each. And they'll prove each shard more or less independently, and then they'll recursively aggregate the proofs because you can't tolerate like 1,000 different SNARK proofs. That's just too big, so you'll sort of squish them down into one proof. Okay, and this introduces complications, surface area for bugs, because recursion means taking a SNARK verifier and sort of turning it into a circuit and proving you know a satisfying assignment to that circuit. And it also introduces some prover overhead because you have to do proving work to prove you know the proofs, right? And so, ideally we wouldn't have to do this. And it's long been known that with some check-based SNARKs, you do not need recursion to keep the prover space bounded. Okay. Now, in general, this results in a prover slowdown. So it's like you have like a very fast prover that uses linear space, or you have a quasi-linear time prover that uses small space. But it seems that with twist and shout, the slowdown to keep the prover space low is really minimal. Okay. And what's going on here roughly is like if the Jolt prover is doing like 500 T field multiplications, T is the number of cycles proved. In linear space, then when we bring the prover space down sublinear, it sort of does an extra like 12 T log T. Okay, and I'm actually familiar with some really nice work coming up that will actually turn this log T into a log T. Okay, which I'm quite excited about. But even with it being a log T, the point is that think of T as like 2 to the 30, right? So you're looking here at like 30 times 12. Versus 500, right? So even though the T log T dominates asymptotically, concretely it doesn't, right? It's like a 50% slowdown, and then further improvements are going to mean we're not even paying a T log T there, yeah. So and intuitively, why is this? It's like generally there's kind of 2 algorithms you can use to implement the sum check prover. One is for what I call dense sums, where you're summing up a bunch of things and like all of them are non-zero. And that tends to be linear space. And then there are algorithms for sparse sums, where you're summing up a bunch of things and most of them are 0. And somehow the sparse algorithms are directly streaming, like they just are streaming. And twist and shout are all about embracing the sparsity. So we just kind of get streaming with minimal overhead. Okay, so this hopefully, yeah.
Does the log T result, does it change to 12? Or?
I think it does. It does. And why is that? It's because we have other optimizations in Jolt. So like in Spartan in Jolt, that's what we use to prove the R1CS. All of the values being summed are small, and so we've come up with some nice techniques to sort of not sort of pay for the first few rounds of sum check, and those techniques, this is some joint work with Kwang here, Kwang Dao, and others, and Giacomo is on the log T work. Sorry, I don't know all your co-authors, Giacomo, but they combine non-trivially. Okay, so it's like the techniques that got this 500 down to 500. they also improve the overhead that comes from moving to streaming. So everything sort of comes together to sort of magically make streaming work out with really, really low time overhead.
You're counting also group operations in here?
No, so this is all of the field operations in SumCheck, and yes, so it is counting the group operations as field, so it's like each group op is like 10 field ops or something like that.
And it's inside that?
Yes, yes, this is all inclusive of everything, yeah.
Okay.
Yeah.
And how you're doing p-pincher? You're doing
Yeah.
p-pincher in chunks?
Yes,
Okay.
yeah.
Sorry, so when you move to lattices, the numbers here changed quite dramatically, right?
Yes. So look, these are just field multiplications, and when we move to lattices, the hope is we'll just work over fields where these multiplications are cheaper, and we won't pay anything else. That's the hope. We don't know how to do that perfectly yet. We're so yeah, the counts will be more or less the same, but they will. It's just each individual thing we're counting will be cheaper. Yeah. Okay. Other questions? Okay. Great. So let's get to twist and shout. All right. How do they work? I guess I do want to say just a little bit about the technical things that make them up. So let me just talk about elliptic curve-based commitment schemes very briefly. If I want to commit to a vector x, think of this x as like the coefficients of the polynomial I'm committing to. What we do with these elliptic curve commitment schemes is we stick the entries of x in the exponents of group elements. And so if an entry of x is 0, any group element to the 0 is 1, and then it just doesn't change this final product, the final commitment. So the zeros just get filtered out. They literally don't change the commitment. That's what I call free commitments to zeros. Okay, and so yeah, I just that's an important point here. And so the commitment scheme we're using in Jolt today is called Dory. It's due to Jonathan Lee from a few years ago. And so the zeros don't change the commitments. If you commit to one other nice thing about Jolt and these SumCheck-based SNARKs is the prover only commits when they commit. The non-zero values are not arbitrary field elements; they're all small. So committing to those values is very fast. Verifier time is logarithmic. It's no trusted setup. The evaluation proofs are also fast to compute, right? So it's sort of asymptotically anyway, you got kind of everything you would want out of a commitment scheme, other than the proofs are like logarithmic instead of constant or whatever.
The prover is doing a pairing for a multi-pairing.
Yes. Okay. So let me elaborate on evaluation proofs are fast to compute. So the evaluation proofs, essentially, the prover just evaluates the polynomial at the requested point, which is sort of you can't avoid that. And then the prover does square root n pairings, where n is like the size of the committed polynomial.
But this changes the group operations. They must be much higher than 10 per.
No, because it's square root n. So each pairing is expensive. You should think of this also as like an economy of scale thing. One pairing is expensive, okay? But if the number, like the prover is doing, work that grows linearly with the cycle count, the number of pairings in the Dory evaluation proofs grows square root with the cycle count. Okay. So for small cycle counts, the pairings are a bottleneck, right? Because one pairing is expensive, but for once the cycle count t is big, square root t pairings is negligible compared to the order t work everyone else does. I mean, the rest of everyone else, meaning the rest of the Jolt prover. Okay. So look, the comparison is between
I'm interested. I would be curious about the complete performances of 2 to the 30.
Yeah. So okay, yeah.
We don't need to go into it now.
Okay, yeah, sounds good. So I would, just as an example, we're seeing that in Jolt at 100 million cycles proved, the evaluation proof is 7% of the Jolt prover time. Okay, and we have knobs to toggle that, right? So for smaller cycle counts, when this would be more than 7% of the Jolt prover time, we can actually turn a knob and it'll fall back to 7%, and some other costs will rise a little bit. Right? And it's always you're balancing some kind of fixed cost and some kind of per cycle cost, and you can always sort of turn knobs so that they're about equal. Yeah. Okay.
Yeah, I know, it's interesting.
Okay.
Sorry, another question.
Yeah.
Are you able to say abstractly what properties of a polynomial agreement scheme would you need to make the rest of the architecture work? So you mentioned, for instance, committing to zeros is important. Is that it's enough to have, I don't know, a homomorphic agreement scheme, and that's it, and the rest. What else?
Yeah, so here are the things we're exploiting in the commitment scheme. So I kind of listed them all with Dory and then plus homomorphism, right? So
like transparency, okay, fine, whatever.
Yeah.
Like it is what it is.
Yeah.
I'm trying to understand from a kind of a.
You need a small values property too.
Sorry.
You need a small values property too.
Good. All right. So that too.
yeah, yeah. And if you give up one of these properties, it's not like Jolt doesn't work, it's just things get slower.
Yeah.
The homomorphism we're exploiting quite a bit. So the prover, right now we're having the prover commit to like 19 different polynomials or something, and batch them all together for one evaluation proof. And so if we didn't have homomorphism,
It would hurt the opening.
it would hurt the opening proof. Yeah.
Okay, so it's like zeros, small values, and homomorphism. Like these is.
Yeah, and again, it's not that things just stop working. Things just don't get as nice if you give up these properties. Yeah. And I guess I could say, and we'll see I don't have much time left, but there's a lot of we do get rid of some zeros. We just don't get rid of all of them, right? We get rid of just enough zeros so like the commitment key isn't too many gigabytes in size, right? Or the evaluation proofs are not a bottleneck. So we get rid of enough zeros so that these two things are not a problem. Whereas prior sparse polynomial commitment schemes or whatever, they literally kind of got rid of all the zeros, right? The prover would commit to like a dense representation of the polynomial, and we're not going all the way down to a dense thing. Does that make sense? We're leaving at least some zeros there. Yeah. Other question? Okay, yeah, so let me tell you, I'm almost ready to tell you how shall works. So we need the notion of multilinear extensions. So if you have a function whose domain is like 0, 1 to the L, right, there is always a unique multilinear polynomial that agrees with that function everywhere it's defined, right? So here's a picture. Here's a function whose domain is 0, 1 by 0, 1. And here's the unique multilinear polynomial that if you just evaluate the polynomial at 0, 1 by 0, 1, it agrees with the function. But the polynomial, of course, you can evaluate anywhere in the whole field. Okay, and if I have a vector, we can talk about its multilinear extension by just interpreting it as the evaluation table of a function whose domain is the hypercube, and then taking the multilinear extension of that. All right, and now the sum check protocol, it's come up many times this week. Today, just think of it as, a magical protocol. Don't worry about how it works, where the verifier is given query access to a polynomial g, say in L variables, and it wants to sum up all of g's evaluations over the Boolean hypercube. Right? So if the verifier did it on its own, it would have to evaluate g at 2 to the L points and sum the results. But the sum check protocol lets the verifier force that work onto the prover, and the verifier winds up just evaluating g at a single point. Yep, okay. And just the only thing I'll say about sum check proving time is, in general, we know algorithms where the prover's runtime grows with the number of non-zero terms in the sum. Okay, so if you have a sum where most of the terms are 0, it's like, to compute the right answer, you can just ignore the zeros, and we can kind of keep that property sort of round over round of sum check. In general, you might pay this log t factor overhead. In twist and shout, at least in shout, you don't pay that overhead. Anyway, don't worry about it. Okay, so now there's just one more concept I want to convey, and then we'll finally see shout. And this is a notion of a virtual polynomial. Okay, so a virtual polynomial is sort of a polynomial that is not committed, but the verifier can kind of pretend is committed. Okay, and what do I mean by this? So in any PIOP, and sum check based ones in particular, like the only information the verifier ever needs about a polynomial arising in the protocol is like one evaluation of it. Right? That's like the definition of a polynomial IOP. Okay, so let's say there's a polynomial and it's not committed, but we can express any evaluation of it as a big sum of other polynomials that are committed, or that are just sort of public and the verifier can evaluate quickly. Right? Then when it comes time for the verifier to evaluate this thing that's not committed, it can just apply sum check to force the prover to tell it the evaluation. At the end of the sum check, the verifier is going to have to evaluate some other stuff, and those things the verifier can get its hands on the evaluation. Right? So that's a virtual polynomial. This is an old notion. The term virtual polynomial is recent. But from Diamond and Posen, I think it's a nice term to refer to in old notion. Okay, questions about this?
That's GKR, right?
Yeah, that's for example. Yeah. Exactly. Okay, so here's shall. So the setup, remember, is there's some Boolean function f. The prover's committed, let's say, to t different inputs to f. Just for notational simplicity, I got rid of the xi, yi. Now it's just x. And there's some claimed output, for each of the evaluations. And so the funny thing about shalt is the inputs to f wind up committed in a strange format. Okay, it's called one-hot format. Okay, and so what this means is, let's switch to the memory view of lookup arguments. If we're doing reads into memory of size k, okay, the one-hot representation of an address into the memory is just a unit vector, right? It's a vector of length k. It's got k minus 1 zeros and 1 1. That 1 is indicating like what is the actual address I care about for this particular lookup. Yeah. So these are very sparse vectors. All right, and so what the prover actually commits to, the way it specifies these inputs to f in shalt is by committing to this function we call RA for read address, which takes two inputs, the one-hot representation of a memory set. Sorry, not one-hot. It takes an address and a kind of a cycle count as input. And so it spits out 0 unless the jth address is k, is address k. Okay, so here, so k and j here are Boolean, but they're Boolean indexes into, for each fixed j, it's you're indexing into a one-hot, vector. Okay, and so the point is this committed, RA vector, this read address vector, it's huge, but it's sparse, right? It's got these t rows, one per read operation, and each row has exactly 1 1 in it. Okay, and once you commit to RA, we can make the read values a virtual polynomial, like very directly. And it's just this expression here. So I claim that if I go to evaluate the multilinear extension of the read values at any point, it's just this sum. Okay, and this is very easy to check. Think of whenever you see a claim like this, right, you just have to check two things. The right-hand side is multilinear, and it agrees with the left-hand side at all Boolean inputs, right? Because the multilinear extension of a Boolean function is unique, so if I give you two multilinear polynomials that agree over the Boolean inputs, they're the same. So what this is saying is for any cycle R, the value output, by f on the rth input is just the sum over, memory addresses of, did the rth read go to that address, and if so, just spit out f at that at that address. I'm sort of mixing the memory view and function view here, but that's it. That's it. And so because this holds over the whole hypercube, it also holds over the whole field, right? So that's it. So the point of shalt is just to make RV a virtual polynomial, right? Like a lookup argument is just trying to have the prover prove that the read values are correct, but the way PIOPs work, all the verifier ever needs is one evaluation of that polynomial. And so this is what the prover and verifier do when the verifier asks for that evaluation. Okay, that's it. And so, RA is committed, and these Fs are structured, and so at the end of this sum check, we're done. Everything's good. All right, so there are a few details I have hidden. Okay, so one is RA is supposed to be one hot. So for every Boolean input R, there's supposed to be exactly one K that is 1, and the rest should be 0. Now this is a little bit annoying because there are K times T inputs. We have to check our Boolean and ultimately one hot here. But it's a very, very, the one hot structure saves us, right? Even though there are KT things we have to check, only T of them are non-zero, and so the sum check prover never pays more than T. Okay, so this is leaning into the sparsity, right? Sum check provers only pay for the non-zeros. Okay, so to summarize, this is shalt. So the prover begins by committing to RA, computing the sum check messages in this sum check right here, also a separate sum check for one hot checking, and then it produces an evaluation proof for RA. That's it. And so, this sum is over it's over k terms, so that's a fast sum check. It's just k terms in the sum. I already explained that the checking. Sorry. Okay, I'm running out of steam here, and I'm also out of time. So let me just say, sparsity saves you everywhere. You commit to RA fast because it's sparse. You can compute this sum quickly because things are sparse. You prove one hotness quickly because it's sparse, and then the evaluation proof is all this Dory stuff that we talked about. Okay, and the last little trick I guess I'll tell you about is, all right, in order to make sure that the Dory evaluation proof is not a bottleneck, okay,
I said pairing, but there is also G1 and G2 operations for log rounds, right?
Yeah, so the Dory evaluation proofs are square root, polynomial size pairings, and square root polynomial size scalar multiplications.
In G1 and G2 for each round.
Yeah.
That's a lot, yeah.
Yeah, but concretely, they're actually cheaper than the pairings. Yeah, one pairing is 10 scalar multiplications or so, and so it works out that way. So if we were dealing, if k was really 2 to the 64, okay, then keep in mind we're applying Dory to this giant sparse vector, right? So as I've been describing it before, this vector has size capital K times capital T, right? And capital K might be 2 to the 64, and T might be 2 to the 30. So you're talking 2 to the 90. So square root 2 to the 90 pairings, it's not going to work, right? So we do need a way to address that. And so this is the final idea I want to tell you about. We introduced this parameter D, which I foreshadowed before, which is controlling sort of commitment costs. We call it the dimension. That's what D is for. And the key observation is that any one hot vector is a tensor product. It can be written as a D-fold tensor product of one hot vectors. Okay, so we actually have the prover commit to these RAIs that each have length just like k to the 1 over d times t instead of k times t. And then we're making RA here a virtual polynomial. So when the Schaup verifier needs to evaluate RA at a random point, it just applies sum check to kind of reduce the evaluation of RA to an evaluation of the RAIs.
The evaluations.
One evaluation per RAI, and they're D of them. Yeah. And then we would, actually we would do this reduction not with homomorphism, but anyway, we would reduce for all of the polynomials we need to evaluate. We batch them together, so we only do one evaluation. Yeah. And that leverages both homomorphism and some, nice sum check-based techniques to do the batching. You use sum check to reduce many points to one point, and then homomorphism to reduce many different polynomials at the same point to one polynomial at one point. Okay, so thanks for letting me go over and generally keep talking until I'm out of steam, and I will just, maybe, is there anything? Yeah, I'll just stop here. Thank you.
You called it a zkVM, but is it zk?
Not today, but it will be. And one of the nice things, well, I guess, how do I want to say this? The elliptic curve-based things can be made zk with really, really minimal prover overhead. So that's the plan. If we weren't using elliptic curves, I think there might be a little more overhead to make it zk, or what you can do is, wrap the non-zk thing in the zk thing. But since we're using elliptic curves, it's really quite easy to make it zk and no prover overhead. Other questions?
So the thing that saves you also here is that the commitment key is also square root size because of Dory.
Yes, and I will say in terms of how we set this D to control, we're doing it to control the commitment key size and the evaluation proof size. The evaluation proof is more of a bottleneck on what we can take D to be than the commitment key. Yeah. So the hashing-based schemes are nice in that the commitment key is like nothing. It's just like a hash function, but then you don't get the free commitments to zeros. So.
And so that would be at the 54, or?
Right now, yeah, and we will move over to BLS 12381 eventually, just for the higher security level.
but you let the prover
No. So actually, the way people typically prove these things is they will run the computer program kind of single-threaded, serially, just because if you don't know anything about the computer program, you can't parallelize it, right? And then once you have the computer program run from start to finish, now you can start proving it, right? And all of that extra work that in proving it can be parallelized, as much as you want. Okay, so we're kind of treating the computer program as single-threaded already, even if it's parallelizable, and we don't. The only thing you gain by assuming it's you actually gain something assuming it's parallelizable. You make the native execution faster. For a little bit of time, people were worried about that actually as a bottleneck, but they figured out how to do it better. So yeah, anyway. So yeah, we're kind of treating it as a single-threaded program already, and just parallelizing the prover. Does that make sense?
Maybe just as a TLDR, sorry, maybe you addressed it in the first slide, but in terms of your main competitors, what's TLDR? Is it faster, slower? What's it?
Yeah, so I claim it's faster, as everyone does. No, you can run these things. So here's how I think about things. I think the right target to optimize for, as like a SNARK designer, is this total prover overhead measured in CPU cycles that I had. Because everything parallelizes well, right? And also through some cosmic coincidence, in my view, the right techniques to optimize the CPU cycles tend to also make things simpler and more parallelizable and all of that. Okay, so on this metric of prover overhead that I prefer, that just means run the thing single-threaded. And I don't think it's controversial that Jolt with twist and shout will be significantly faster by that measure. And then we will have to go through the pain of GPU integration and all the other bells and whistles on top of that, which will take some time. Is that a clear enough answer?
Well, but like for example, for this Ethereum challenge,
yeah.
What would be the current number? So I don't know.
Yeah. Okay. I mean, so right. So we're not hooked up to that challenge yet, and here's what has to happen for us to get there. So firstly, we need the memory to come down a little bit because we can't prove 1 billion cycles on the well, we could do it on like with a terabyte of memory, right? Yeah. But that competition is very focused on dollar cost of proving a block, and you're not going to be win on that metric unless you're using GPUs very effectively, right? Because GPUs are kind of just the cheapest dollar cost per compute. And so you just have to go through all of the work of squeezing out a really, really good GPU implementations, tons of engineering, or you just won't be competitive on that. So we just have to wait till we get to that point.
Right.
Okay.
Questions outside?
Yeah, thank you.